All right, this week's characters come right before the birth of calculus. So this is like just 50 to 100 years before Isaac Newton really kind of solidified these core ideas of the derivative and the integral, whatever the heck that is. But today's characters are quite interesting. First off, we got Pierre de Fermat, who was a French mathematician born in the early 1600s, early 17th century. And this guy's kind of like famous because of his equations. For instance, we have Fermat's last theorem, which was only recently officially proven by a mathematician named Andrew Wiles. He famously wrote the theorem or conjectured the theorem in the margin of his notebook. And he said, I have a proof of the theorem, but not enough room in this margin, so I'm not going to write it. So the proof was unknown for like almost 500 years until recently in the late 1900s. A guy named Andrew Wiles officially proved the theorem. It is very doubtful that Fermat had a theorem in his mind because the theorem that it took, or the proof that the theorem took, is pages long. Andrew Wiles, he dedicated really his life to proving that theorem. And it was pages long, so it's doubtful that this guy held a proof in his brain, Pierre de Fermat, 500 years ago, that was sufficient enough. Also, the proof by Andrew Wiles took a lot of advanced mathematics that were unheard of at the time. But he could have, and it could simply be a proof that us as modern mathematicians are missing, but we have no idea if he actually had a good proof, or if he was really flubbing, or if the proof was not actually a proof, but a fake proof. So he was a French mathematician born in August in France, worked as a lawyer and government official while pursuing mathematics privately. In fact, he's famously a horrible lawyer because he spent all of his time doing mathematics. So mathematics was sort of this guy's mistress. He's always messing around with the mathematics when he should be worried about his clients and the people that hire him as a lawyer. But he was famously really bad at being a lawyer because he was spending all of his energy inside the mathematics. He really kind of opened the field of analytic geometry. Him, along with Descartes, who we talked about recently, really talked about kind of how an XY graph works, or how we can place shapes onto the Cartesian plane. And in terms of our class here, we have this guy really came up with this thing called Fermat's theorem. We know what maximums and minimums look like as long as the derivative exists. So if we have some sort of maximum like this, and we know that this function is differentiable here, then we know that there's no option for the derivative. We know the derivative must be 0. This is really Fermat's kind of idea. Same thing with a minimum. If you know the function has a minimum, and you know the function is differentiable at that minimum, then you know that the tangent line is horizontal. In other words, you know that the derivative must be 0. He really is famous for all of his discoveries, a whole bunch of discoveries in the early 1700s. But in terms of our class right now, we are trying to kind of develop a way to analyze graphs, and through Fermat and his theorem, Fermat's theorem, which was proven in class recently, we now know if we have a differentiable function that has a maximum, we know that the derivative must be 0 there. And how this is useful for us in particular is we can seek out these maximums and minimums by taking the derivative, setting the derivative equal to 0, and see where we have these horizontal tangent lines. And once you have these possibilities for maximums and minimums, you can investigate further and to see if those actually are maximums and minimums. Notice that we have to be a little bit careful because this could happen. Notice we do have a horizontal tangent line, but that is certainly not a maximum or a minimum because you have part of the function that's above that line and part of the function that's below that line. Whereas in this case, the function's entirely below the tangent line. In this case, the function's entirely above the tangent line, except maybe at this point. So in other words, Fermat's theorem cannot really be reversed in the nicest way, but it at least helps us seek out where these maximums and minimums could occur. Here's some of his actual writing, and here is his tombstone, where you can see that you have Fermat's last theorem there on the tombstone. It's actually really easy to say. Oh, spoilers. Fermat's last theorem says a to the n plus b to the n does not equal c to the n if n is bigger than 2. So there are no solutions to, for instance, this equation if a, b, and c are positive. So a cubed plus b cubed does not ever equal c cubed. Like, it can't happen. So that's what Fermat's last theorem is, and he's famous for all of this work, and how he affects our class is this work with derivatives. He didn't call them derivatives at that time, but he had his own methods, just like Descartes did, for finding derivatives and finding these local minimum and maximum values, which were just very, very quickly in the latter half of the 1600s developed into an actual theory, and that is the theory of calculus due to Leibniz and Newton. Speaking of the theory of calculus, there was a mathematician that famously hated calculus. He thought it was completely, fallacious, just wrong, full of contradictions. And that mathematician was Michael Rolle. Ironically, he actually contributed to the development of calculus quite a lot. He's famously known in our class as the inventor of Rolle's theorem. Rolle's theorem says something along the lines of, if you have a function that has the same height and you know the function is smooth, then there has to be points, very similar to Fermat's theorem, there has to be these points where the tangent line is horizontal. That's what Rolle's theorem says. But he was actually, as I said, he hated calculus. He thought it was ridiculous. Notice that he was alive, really, when calculus was birthed. So tangentially, no pun intended, he was not liking these new ideas from Isaac Newton and Leibniz. He's saying, this is all ridiculous. You can't be talking about infinity so ridiculously. But he also, at the same time, developed some of the core theorems at the heart of calculus. Remember that this Rolle's theorem, this guy's theorem, really is the framework for the huge theorem, the mean value theorem. But anyways, he was also a French mathematician born in the mid-1600s. He mostly was self-taught, and his beginnings were very modest. I'm pretty sure his dad was like a school teacher. No, a shopkeeper. He became a member of the French Academy. He, of course, discovered what Rolle's theorem is, and he developed algebraic techniques for actually locating the roots of equations. He was deeply skeptical of the new calculus. He preferred concrete algebraic reasoning over infinitesimals. He didn't like this idea of the infinitesimals that Newton and Leibniz were working with. He was very persistent and determined. He solved a lot of Diophantine equations, which are these famous equations in number theory. And that's kind of what brought him into the limelight, is his capability of solving these unknown equations. And he, because of those solvings, he came into the intellectual sort of prominence. And as we said, his theorem, ironically, became one of the core theorems of calculus, despite his critique of the theory. He invented Rolle's theorem. And let's see, anything else I want to say about Michael Rolle? I guess not. Overall, these two, Fermat and Rolle, are huge in what we call curve sketching, which is this week's topic. Knowing how to, because of derivatives and because of second derivatives, we can discover a ton about the curve or the graph of a function. And if we can investigate with this tool of the derivative, which is pretty much a slope machine, if you really understand the slope of a function, then you can really understand the behavior of the function at any point. Further, if you know how the slope itself is changing, then we can investigate further in terms of like concavity and things like this. So overall, Fermat discovered that the local extrema occur where the slopes vanish. That's what this stuff is right here. Pierre de Fermat says local extrema, if it occurs and it's differentiable, then the slope is not actually there. In other words, well, the slope is zero, not that it doesn't exist. I should be more careful. Well, it's either that the slope is zero or the slope does not exist. In other words, if you have a local extrema, then you have a critical point. That's really what Fermat's theorem says. Whatever the heck a critical point is. Well, we know what a critical point is. A critical point is an x value on the graph where the derivative either does not exist or equals 0. That's what a critical point is. Rolle proved that such zero slopes have to occur between equal function values if you have a continuous differentiable function, which we do in this drawing case right here. Much later, Lagrange, who we will talk about next week, generalized Rolle's theorem to create this thing called the mean value theorem. And a little bit later than Lagrange, this guy named Cauchy gave the first rigorous proof of the mean value theorem, which we saw in class. The mean value theorem is pretty much the core theorem of differential calculus. That is, and it explains how derivatives control the overall behavior of functions. Because of the mean value theorem, we are able to generate a whole bunch of machines that allow us to shed light onto how a function behaves. This theorem really is the backbone of curve sketching, optimization, and hundreds of proofs in calculus, and its beginnings kind of have the spark of the theorem come from these two men, Pierre de Fermat and Michel Rolle, both French mathematicians famous in the 17th century.